Hello, everyone, and welcome to our PTV Talks session for today. In today's session, we will be featuring the work of Joe Devore from KLJ Engineering on using SSAM and Vissim to predict future safety. This is our second PTV Talks event. PTV Talks is a series of regularly scheduled web sessions that we recently launched in response to our clients' requests for additional content and as a way to deliver product information, use cases, training material, and other educational information out to our users. Throughout this series, we will have PTV staff, clients, and other industry professionals presenting on various topics. We would certainly appreciate your feedback on what type of content you would like to see, so please feel free to submit any requests or comments to info.us@ptvgroup.com. We do currently have two events scheduled for next month as well. On May 9th, we will be hosting a Vissim Product Management Hot Seat, where we will have users discussing feature requests with our Vissim Product Management team. And on May 23rd, we will be showcasing some of our user presentations from last year's user group meetings. So please watch your emails for links to register for those events, as well as some additional details. Just a couple of quick items before we get started. A recording of today's presentation will be made available within the next day or so. That will be posted to ptvtraffic.us under the Resources tab. There will also be an email that goes out to all attendees tomorrow with a link to that information. For questions, you are able to submit questions through GoToWebinar, so please feel free to submit your questions. We're going to hold all questions for Joe until the end of the presentation when we will have a Q&A session. And with that, I will turn it over to Joe.
Thanks, Adam. So I'd like to start out by thanking PTV for this opportunity to give this webinar. Been using PTV Vissim for over about 8 years now, and I like that they offer these types of webinars to really get down into the weeds with modeling, and it's fun to both present and learn more about these types of applications of the software from different users across the country and across the world. So with that, I'd like to start out. I'm giving a presentation today on the kind of combination of using SSAM and Vissim to give a better idea of both existing safety and really to provide a quantifiable future safety analysis that we can use in both looking at what's going to happen to existing crash rates in the future and also kind of comparing alternatives and really having a good basis for our safety choices for future improvements. So as we get into the presentation here, we'll talk about some of the existing strategies that are out there today. We'll get into the specific SSAM approach using FHWA's software, and then we'll provide some project examples at the end showing kind of the diverse options that you can use this safety analysis for in your projects. So starting out with kind of the existing safety techniques, most traffic engineers know how to provide a critical crash rate, looking at kind of those previous 5 years or 10 years of crashes at an intersection or roadway segment, and then calculating a critical crash rate from that to see if there's an issue over kind of that statistical average versus a state or other crash data set. This usually shows whether there is an existing issue at an intersection and can really prompt the need for a project based on safety. As we start looking at putting in improvements at those intersections or segments that have that critical crash rate or above the average crash rate, we look at putting in crash modification factors of different alternatives or different improvements. And these are usually from previous studies, which may or may not mirror the site-specific considerations of your study intersection. A couple of the other tools out there, FHWA has an ISAT tool that kind of mimics this predictive crash safety performance functions, using those CMF factors to kind of calculate what happens to your crash rate. AASHTO has their own safety analysis type tool. And then when it comes down to the end of the day, when you have all of these different tools, engineering judgment really does play a huge role in kind of what safety benefit are you expecting from these improvements. Over there to the right, we also look at kind of crash values. When we're looking at improvements, are they worth kind of that benefit to cost ratio of improving? MnDOT publishes these every year as far as what the cost of a crash is, so that we can really look at improvements that try to minimize that cost to us as a society. But when we really look at the basis of all of these future crash analysis techniques, CMF data is really at the basis of all of those. And what happens with the CMF data is, because it's based on a number of different studies, some of these improvements have quite a big range of what that expected safety benefit is. So two examples I pulled out. One was a DDI interchange, kind of converting an at-grade or diamond interchange to a DDI. And I just pulled all of the crash type, crash severities that kind of lined up where they were all the same. And even with kind of filtering out some of those crash rates, we still have a range of about 0.54 to 0.81 CMF factor. So that's over a 30% or about 30% difference in those expected safety benefits for that type of an interchange. J-turns or reduced conflict intersections show an even greater range of a safety benefit when you start looking at the applications, between 60% all the way down to only a 13% improvement, which makes a big difference when you have some of those higher injury type crashes, and really can skew your final preferred alternatives one way or another based on which CMF factor you're choosing. So this was what really prompted me to look for other tools that are out there. And one of those tools was the IHSDM, the Interactive Highway Safety Design Manual, or model, which kind of has more of a design focus. It has different inputs such as the horizontal alignment, vertical alignment, lane offsets, shoulder sections, design speed, driveway density. And when you start really looking into these details, there's a lot of spots where if you don't have that level of detail, you're really still guessing, and there's a lot of variability in those values and what your final answer might be coming out of a safety analysis like this. So this is really more of a segment-based software that's really looking at kind of those final design type safety benefits. And it does a very good job of including runoff road type crashes and really looks at all of the different crash types you could look at. But there still are some holes when we're really looking at kind of that preliminary, looking at 3 or 4 alternatives and trying to pick which one's best for us as traffic engineers. So getting into the SSAM modeling approach, this is an example from Bemidji, Minnesota, where we used a company called MicroTraffic to really start looking at the existing safety and existing conflicts on one of our study corridors. And so what we did with this data is we're trying to quantify the existing near miss data that's happening on these roadways. And as you'll see in these 3 or 4 examples, these vehicles are only having about a 1 to 2 second gap where they're getting across traffic before another vehicle kind of intersects that trajectory. And so by quantifying these near miss type conflicts, we can start looking at what truly is the existing conflict potential of that intersection. And in this example, real close, again, that kind of permissive movements and crossing movements, These are the most dangerous when a vehicle makes a mistake, you know, a second or two earlier or later could cause a pretty serious crash. So these are the exact type of conflicts that we're trying to minimize through our design of improvements to try and improve the safety at both the intersection and the corridor as a whole. So getting into the surrogate safety assessment model basics, the conflicts are broken up into three types: crossing conflicts, lane change conflicts, and rear end conflicts. So crossing conflicts are basically anything between a right angle to a head-on type conflict in the trajectory file. A lane change is when vehicles are shifting lanes kind of between that right angle about 30 degrees. And then a rear end type conflict where one vehicle is kind of coming up behind another vehicle, and if they didn't make that braking decision in time, they'd end up rear-ending the vehicle in front of them. SSAM also does a good job of allowing you to calibrate time to collision and post-encroachment time. So time to collision is kind of that front gap ahead of a possible collision. And we are looking at everything from 0 seconds to 1.5 seconds out of VSIM. And then that maximum post-encroachment time is more for rear-end type conflicts, where we've actually taken that down from the default of 5 seconds all the way down to kind of 1 or 2 seconds to better validate from our existing data in our models. And then also SSAM allows you to really take vehicle type into account, looking at PED analysis, bike analysis, transit analysis, specific roadway links, and we've even used it on freight analysis for some of our models. So the SSAM analysis really starts out with how are you coding your VSIM models. VSIM is by far the best tool to use with the SSAM because it's literally checking one box in your evaluation configuration to output this trajectory file of the vehicles. So it's very important to have your sensitivity at that 0.1 second so that we're really getting a good, you know, time step period, or we're getting those 10 time steps per second to really look at the interaction between vehicles. It's also important to keep those constant parameters when you're modeling. Having a guide to go by for priority rules and conflict areas where these vehicles are interacting is very important in kind of keeping your models the same as you're comparing alternative to alternative and you know, increased volumes in future models. Also doing kind of that realistic VSIM calibration, watching your models, making sure you don't have vehicles crossing other vehicles is very important. Making sure signal timing's correct. All of these lead into, if there's a mistake in your VSIM model, you're going to have a situation where one spot really pops out as having a safety issue in the SSAM analysis. Also basing your priority rules on critical headways from HCM is important to really give that variability in some vehicles having kind of that aggressive behavior at unsignalized intersections or permissive movements, and then some vehicles having that more conservative nature too when they're interacting with other vehicles. Specifically, a couple of intersections I've pulled out, mini roundabouts and roundabouts. Those are very important to look at larger vehicles, WB62s going through, where you might need an additional priority rule to allow that vehicle to clear out of an intersection before that priority rule allows another vehicle to enter it. If you think of kind of the real life application of a mini roundabout, if there's a large size truck in the roundabout, you're probably not going to try to pull into the trailer of it. You're going to allow it to get through the roundabout and then have that priority rule. So really taking a look at the modeling, looking at those kind of crossing gaps and really trying to get those as realistic as possible is very important. Same thing with flashing yellow and permissive movements. We code these as having the signal group in the priority rule, so that when that signal group turns yellow for, in this case, that phase 2 direction, the left turn will actually make that movement on yellow. And if one of the eastbound or westbound through vehicles does go through that yellow light, we're actually going to have that crossing conflict. And that's what gets quantified in some of our signalized intersections, that conflict that leads into what we're looking at to try to prevent in some of these modeling exercises. So the basic model validation for SSAM was done by FHWA. They had quite a few different intersection and interchange designs that they looked at. And they came out with kind of a general conflict to crash ratio of about 20,000 to 1. So 20,000 conflicts in the model end up being about 1 crash in real life. They had similar correlation with kind of the existing data between what they were looking at in modeling exercises and what was actually happening out with, 5-year or 10-year existing crash analysis. But we actually went through, and before we really started using this on a lot of our projects, we wanted to kind of create that validation too. So some of these are projects that we worked on in Minnesota, one up in Brainerd, Minnesota, one in Bemidji. But we really started looking at the total vehicle conflicts out of Vissim and how they compared to the crashes per year that were actually happening. And so when you look at kind of that 11.9 and 8.2 and then the 63 versus 45, our modeled conflicts were actually a little bit higher than the crashes that were actually happening out on the corridor. And so that's more attributed to kind of that rear end and lane change. And we were able to kind of fix a little bit of that through adjusting the post-encroachment time to kind of bring down those rear end type conflicts and better match that existing crash rate for our existing models. But what we also noticed was when we looked at only the crossing conflicts happening on these projects, we found that it was a much better comparison between what was being modeled and what was actually happening out in real life. And throughout this presentation, you'll hear me talking more in detail about these crossing conflicts, because these are the right angle type crashes or head-on type crashes that are usually most severe, and we really want to avoid these and kind of look at the reduction of these more heavily than the other conflict types. So getting into some of the project examples that KLJ has worked on. One of the projects up in Bemidji, Minnesota on Highway 197, we had a very high crash rate on this corridor. There were 45 crashes, and a lot of these were serious injury type crashes, costing the community $1.6 million per year. As you can see on the bottom, there are 8 signalized intersections, a couple of major minor approaches that had significant volumes. Those unsignalized locations had kind of that 20 to 40 seconds of delay for those left turns, and this was projected to increase to almost a minute per vehicle of waiting to make kind of that left turn movement out of these accesses. Another big part of this project, we had over 100 businesses served on this corridor, and access was very important to all of these businesses. There were almost 60 accesses in about a mile spacing on this corridor. So it really was an access management type project that we were dealing with, and we really needed a way to show the safety benefit of reducing and consolidating some of these accesses. So when we looked at the existing conflict analysis for this project, rear end conflicts were a very high percentage of the total conflicts on the corridor. These were happening out in kind of the west end of the corridor, where there were high vehicle traffic, high speeds, and signalized intersections. So when you mix kind of all three of those together, you do end up with a lot of rear end type conflicts, and those did match what we were seeing in the existing crash data too. However, we also do see quite a few crossing conflicts and lane change conflicts being a part of this project. Specifically on the east part of the corridor, where there were a lot of protected permissive type signals that you can see at Irvin Avenue, where we had a lot of crossing conflicts. And then in the major retail sections where there were a lot of business accesses, we saw a lot of lane change and crossing type conflicts not at those major intersections. So as traffic volumes grew, we saw the conflicts grow quite substantially more than just the linear traffic growth. So for 2040, we had about a 25% traffic growth rate. And then we also had an alternative that showed kind of the peak recreational volumes too along this corridor, which was about a 40% growth rate over that weekday existing period. And what we saw in those crashes is that the crashes for that 2040 no build were over two times as much as the traffic growth. And for the summer rec period, it was 3 times just the traffic growth. And what that is as that traffic grows, the gaps don't decrease linearly, they decrease exponentially. And so it makes it harder and harder for vehicles to access the corridor, leading to more of these conflict types and severity along the corridor. So when we started looking at alternatives for this, we looked at some medians. We looked at redoing the signals to more protected movements. For one alternative, we looked at kind of roundabouts with a wide median for another alternative. And then 2 alternatives that kind of got thrown out early was decreasing to a 3-lane section and some access consolidation only along the corridor, which both of those alternatives were thrown out early because they were both increasing the crash rate or conflict rate, and they were increasing delay along the corridor. So this Alt-1 and Alt-2 really saw some benefits. Alt-1 with the signalized alternatives, we looked at implementing a bunch of kind of right plus U-turn type movements for the accesses, allowing kind of that 3/4 intersection so that there was a lot more access into a business, and then you had to make that right plus U-turn out of the business. And we actually saw a total reduction in total conflict, but we also saw all 3 categories decrease in that crash rate versus the no-bill alternative. However, in the roundabout alternative on the right side, we actually did witness an increase in total crashes or total conflicts in the model. Rear end and lane change type conflicts increased quite a bit coming into the roundabouts, trying to get in the right lane for roundabouts, getting to and from accesses in the right lane. And so it did promote kind of more of that lane shifting in the total corridor alternative. However, one of the big advantages of alternative 2, the roundabout, were the crossing conflicts were decreased by about 85 to 90%. And when we look at these crossing conflicts, these are the severe injury type crashes. I'll go back to that a lot through this presentation, where we're really looking at the safety of the corridor. And so what we did in the total safety ranking on the bottom is we gave that kind of crossing reduction about 2 times the weight as the other rear end and lane change type conflicts because of that improvement in the severity rate. And so that ended up showing that alternative 2 was one of the best safety improvements for this corridor. Another project that we worked on was up in Brainerd, Minnesota on 371. And again, it was kind of an access management study. We're really trying to show the benefit if we are taking away access from business, what is that safety benefit to vehicles going through the corridor and getting to and from that business still. This specific project had a lot of event and recreational traffic with Brainerd International Raceway along the corridor. So there's about 100,000 people that come out to events during the summer at Brainerd International Raceway. So there's a lot of traffic coming in and out of this approach. There were critical crash rates at both county roads on the bookends of the corridor, but traffic signals weren't warranted along this corridor. So MnDOT's previous recommendation had said just put a traffic signal at both of these intersections, but there was really a re-looking at this intersection because it wasn't going to meet those traffic signal warrants. So when we really started looking at the SSAM outputs for each alternative, we noticed that crossing conflicts were, again, quite high with these unsignalized side street stop approach, full access intersections. And because there were about 7 or 8 of these along this corridor, drivers along 371 had a hard time knowing where traffic was coming out of, and wasn't really spreading the conflicts out throughout the corridor, as you can see in that vision on the left side. As we started looking at different alternatives, we really saw these consolidating access plus implementing these RCI type intersections, so the right plus U-turn, cut down these crossing conflicts by 90%, 95%. The total safety benefit, kind of looking back against those CMF factors I brought up earlier, looking at that CMF between 13 and 61%, we actually are decreasing those total conflicts as well, about 49%. So that's kind of right in that range. It gives us a lot better idea of what this actual safety benefit would be along this corridor. And again, looking at those crossing conflicts, the huge benefit in taking away all those crossing conflicts except for the left in at those 2 major intersections. So kind of looking at our proposed alternative, you'll see that traffic isn't making those full access type movements. You're not getting that 2-stage type crossing. And overall, it's a lot better of a corridor for limiting those conflicts. So for the future alternative, we did propose 5 RCIs from those 8 existing intersections, allowing those vehicles to make the right plus U-turn movement, which really only creates those crossing conflicts for the U-turn movement and the left turn in movement. And on the right side, you can see that with the volumes that were in the model, these crossing conflicts were almost non-existent for this specific alternative. Our third example that we have, it was a lot higher volume than the previous examples. This was in Mankato, Minnesota, so south central Minnesota. 6 critical crash intersections were identified along this corridor. 2 of those being existing multi-lane roundabouts at Adams Street and Madison Avenue. And really what MnDOT was looking for was, do we continue along with implementing these multi-lane roundabouts, or should we turn this back into a signalized corridor? So one impact with this study is, instead of just looking at peak hour analysis, We wanted to look at 24-hour safety and operational benefits that we could see in the roundabout model versus the signalized model. And so when we modeled this in Vissim, we started to see that, yes, during the PM peak hour, the roundabout modeling did have worse operations than the traffic signals, and there was some queuing, and it was about a 10 to 15% operational deficiency in the roundabout model versus the traffic signal model. And so as we went to stakeholders with this information, they really started questioning whether that no build with the two roundabouts at Adams and Madison was still kind of that preferred vision for the corridor. Did they really want to change this into a full roundabout corridor where there was a mix of both 2x2 and 2x1 roundabouts? And so as we looked at these operational results, you can see from this daily representation of delay that, yes, in that PM peak, the roundabouts did operate worse than the signals, but the other 23 of 24 hours out of the day, we were able to limit that operational delay at those roundabout intersections. Looking at kind of that average delay per vehicle totaled up, the roundabouts actually minimized about 25% of that delay in the signalized model. So kind of looking at this, the stakeholders really felt confident that by 2045, if they were seeing the aggressive traffic forecasting that they were making, they could still implement meters at a few of these roundabouts to really keep that delay under control. But when we looked at safety, the roundabout corridor really was maximizing the safety benefit versus the traffic signal corridor. So for 2030, which was the forecast they felt more comfortable with, we were seeing a 10% decrease in kind of those total conflicts, with about a 15% decrease in crossing conflicts, even having some 2x2 and 2x1 type roundabouts along the corridor. By 2045, although the total conflicts did rise, especially with the meters, we were still minimizing those crossing conflicts, actually at more of a benefit with the roundabouts than with the 2030 volumes. So we were really able to show that, yes, you might have a higher crash rate with some of these roundabouts, which is what they were looking at with existing crash rates, but they are a lot less severe, and you know, the total conflicts are really only going to be about 10 to 40% more than they are today. Our last example here is in Grand Forks, North Dakota. This was on the UND college campus. So we were really looking at ped, bike, and transit considerations along this corridor. Looking at that multimodal conflicts along this 2-lane, 3-lane section. But they really wanted to expand the cross-section to prioritize transit, bikes, and peds, where the original corridor wasn't doing that. So we were able to give the stakeholders kind of this SSAM map of the existing hotspots for where vehicle collisions were happening along the corridor. And they were happening at, yes, the major signalized intersections, but there were also some minor approaches that were showing a lot of crossing conflicts that could be improved with either a traffic signal if volumes warranted that, or a roundabout, or some type of improvement at those intersections. But where SSAM was very useful was really identifying where those ped conflicts were happening. Because this was an unsignalized corridor, there were multiple ped crossings along the roadway where peds could cross and have to stop vehicles. And during major class time arrivals and departures, vehicle traffic was really just going crossing by crossing, having to stop for these PEDs, crossing the road, and it created kind of a, during peak times, vehicles knew to look out for PEDs, but during those off-peak times when there were a lot less PEDs, it was a lot harder for vehicles to see those PEDs and stop. And so as we started modeling, we did notice that there were a few crossing locations that did start to show crossing conflicts that you can see in that bottom right. We were able to just take out those pedestrian interactions out of the SSAM data and really look at where these conflicts were happening. We were also able to filter out that graphic even further because we noticed in the SSAM data that PEDs running into PEDs also quantified as a rear end type conflict. So we were able to filter that data even further to really only look at those vehicle and pedestrian type conflicts. And lastly, when we started looking at those improvements that we were looking at with a cycle track or a bike median and a bus turnout, and then our final preferred option of a shared bike and transit lane, we were really able to prioritize both the University Avenue safety improvements for vehicles as well as those pedestrian crossing locations, and also take into account the cost of the project too, to really pick that solution that had the best combination of all of those. So kind of the final slide I have here is, where do we use SSAM? We've been using it on almost every VSIM study that we do, whether that be a corridor study, an access management type study. We've used it on reduced conflict type intersections. We've used it on roundabout intersections. And then we've also kind of expanded that to looking at pedestrian bicycle safety by being able to filter out the multimodal conflicts and really looking at a good representation of what that future safety of the corridor is going to be. As with every one of my presentations, I also like to pick apart ways to improve the method, really using those daily VSIM results to understand what's happening during the day. We've noticed a lot of benefit in that versus just running those peak hour type analysis. Especially in that Mankato example, we're able to show a lot of benefit outside of that peak hour and really take that into consideration both for operations and for our safety data. Being able to filter the link and lane numbers to determine the mode would be a helpful way in SSAM to really prioritize the software. And then using companies like MicroTraffic for an existing conflict mapping to really understand the existing conflict potential of the corridor, and then being able to tie that into the modeled conflict potential of a corridor was really helpful on our Bemidji project. And then the last bullet I have is being able to export it to GIS. As you can see, some of the graphics I had from the SSAM software had kind of that green screen. It's very hard to match an aerial up to the data in the SSAM software. So hopefully FHWA makes an improvement where we can export those conflict maps to GIS so we can have that aerial overlay to show to stakeholders. So with that, I'd like to turn it back over to Elizabeth and Adam for any questions that we have today.
All right, Joe, thank you very much. A couple things that came up in the questions kind of repeatedly was, for these example studies, did you also do the HSM analysis? And if so, how did those compare? And also, what criteria kind of do you look for in determining whether you use SSAM or HSM on a project.
Yep, so for all of these, we did use HSM too. So that is kind of the using CMF factors and looking at how it compares. It gets back to how confident do you feel in that CMF data? And that was really where we were, not confident in having that range of the safety improvement. We wanted a quantifiable solution to kind of try and pinpoint the site-specific safety benefit. So when we did compare it against kind of that HSM process, we were close one way or the other, and it usually fell somewhere in that CMF range as for the two examples I showed.
Okay. So I see one there for where can you get SSAM? That's available through FHWA. I believe the website's the OSADP website. Their open source developer portal is the best place to get a hold of that.
It is freeware. If you just search FHWA SSAM, it'll bring you up to the website where you can kind of look into some of that previous statistical analysis they've done, as well as go to the download portal for that free software.
Okay. Couple other things. Someone asked if kind of what your methodology was for doing that 24-hour model versus the peak hour model. Do you have any kind of specific pointers there?
Yeah, so what we found out is, it really is a daily safety benefit. Operations, everyone remembers what's happening during that peak hour, but really when you're looking at safety improvements along a corridor, you're really looking at the volume profiles throughout the day, how they interact with each other, and what type of benefit you can have throughout the day, not just for the peak hour. So when you start looking at how they had those estimations for kind of changing conflicts to crashes, it was really important as we increased the number of hours that those conflicts were modeled over to really matching the existing crash rate better. When we were just doing that over 1 hour, we had a very high estimate of crashes per year because we were really extrapolating out the highest volume hour comparable to the rest of the day, comparable to a crash rate per year. So by running that 24-hour model, you have both your peak hour as well as your lower volume hours leading into that crash comparison against your historical crash rate.
Okay. Perfect. Well, Joe, thank you very much. I think with that, we're going to conclude the live Q&A here. Anyone who asked a question that hasn't been answered yet, we will get back to you. We have all that recorded, so we'll make sure to help you get those questions answered. Couple of other things. As a reminder, don't forget to register for the upcoming events on May 9th and May 23rd. We're going to put links to those registrations in the follow-up email that's going to go out tomorrow. That will also include the link to today's the recording of today's presentation, so be on the lookout for that. And again, if you have any questions or comments about this or one of the other PTV talks or any requests for future topics, please feel free to reach out. The best way to submit those is to info.us@ptvgroup.com. And with that, Joe, again, thank you very much, and thank you to everyone for attending, and have a great day.
Thanks, everyone.